When visualizing a molecule, standard ball and stick models fail to capture the probabilistic reality, positively charged nuclei surrounded by a constantly shifting electron cloud. Introduce an external electric field to this system, and because electrons are vastly lighter than the nuclei, that probability cloud reacts and shifts first. If a molecule already possesses a permanent dipole, the field can rotate the molecule to align it. But even without that permanent separation, the field physically distorts the cloud itself, creating an induced dipole. This formula provides the quantum mechanical definition of the electric dipole moment, calculated as an expectation value. The inclusion of these state terms confirms the dipole arises from the full probability distribution of the quantum state, not static point charges. This microscopic probabilistic distortion dictates macroscopic behavior, governing everything from the dielectric constant of capacitors to the refractive index of optical glass. To quantify this electron cloud distortion, we express the induced dipole as an expansion series based on the strength of the applied field. For weak fields, the response is linear, governed by the polarizability, alpha. But stronger fields trigger nonlinear responses, introducing hyperpolarizabilities, beta and gamma, used in advanced optical modulation. Because real molecules are rarely perfect spheres, their electron clouds do not respond to electric fields equally from all directions. It is significantly easier to stretch the electron cloud along the axis of a long, conjugated organic molecule than it is to distort it perpendicular to that axis. This directional preference is polarizability anisotropy. This matrix shows that polarizability must be treated as a 3x3 tensor. An electric field applied in the x direction can actually induce a dipole shift in the y direction. This directional dependence at the molecular scale directly produces material properties like optical birefringence and allows for the control of light in liquid crystal displays. Physical cloud distortion is a direct result of the molecule's internal quantum energy architecture. When an external electric field is applied, it acts as a perturbation, mixing higher energy excited states into the molecule's resting ground state. This sum over states formula translates quantum mixing into polarizability. The numerator calculates transition dipole moments, dictating how strongly the states connect. The denominator tracks the energy gap. If an excited state is close in energy to the ground state, that denominator shrinks. As that energy gap narrows, the resulting polarizability spikes. This explains why heavy atoms and large conjugated molecules are so highly polarizable, while compact elements like fluorine have rigid, hard-to-distort clouds. Polarizability is the macroscopic manifestation of these internal, virtual quantum transitions. If we replace a constant field with the rapidly oscillating electromagnetic wave of light, the molecule's response changes. We call this dynamic polarizability. Because it is frequency-dependent, the response intensifies as the incoming light approaches one of the molecule's electronic transition frequencies. This frequency-dependent response allows us to map molecular structures using different types of spectroscopy. Selection rules for infrared absorption versus Raman scattering show how these techniques complement one another. The top equation states infrared light is absorbed when vibration alters the permanent dipole moment. The bottom equation shows Raman light is scattered when vibration alters polarizability. Because IR probes permanent charge separation and Raman probes cloud distortion, the two techniques provide a complete map of molecular vibrations. This cloud distortion even occurs in the absence of external light sources, governing how neutral molecules interact with one another. Even perfectly nonpolar molecules experience a mutual attraction because their electron clouds constantly undergo spontaneous, correlated quantum fluctuations. These correlated fluctuations create London dispersion forces. They scale with a molecule's polarizability and drop off as 1 over r to the 6th power at short distances. However, electromagnetic influence is limited by the speed of light. It does not travel instantly. This text outlines the retardation effect. At larger separations, the field from the first molecule takes time to reach the second. By the time it arrives, the first molecule's quantum state has already changed. This delay desynchronizes the fluctuations, weakening the attractive force and causing it to drop off more steeply as 1 over r to the 7th power. While short-range dispersion allows noble gases to condense into liquids, these light speed delays redefine the interactions between neutral particles across longer distances. When we zoom out from isolated molecules to bulk materials, we find that these microscopic responses add together to polarize the entire medium. The collective response of billions of molecules determines how the material as a whole reacts to an external field. The Clausius-Masati relation connects these microscopic quantum properties to macroscopic engineering. It explicitly links the molecular polarizability on the right to the macroscopic dielectric constant on the left. While the reorientation of permanent dipoles is the primary factor for water's high dielectric constant, electronic polarizability adds a second layer of response that helps screen the electric field between dissolved ions. Similarly, the Lorentz-Lorenz relation connects this same molecular polarizability to the refractive index of optical materials, such as lenses and OLED layers. The physical properties of the materials we utilize daily are the aggregate result of the quantum mixing occurring within individual molecular states.